Okay, guys, today we'll start with the first part of day one in thermochemistry, and we'll focus most into the energy, as even the focus of this unit on chemistry 30 is regarding the energy. What you have seen and tackled even on the previous courses are two processes that are known as the photosynthesis and the cellular respiration. Photosynthesis is the process that produces glucose, yeah, and cellular respiration is the opposite or the opposite reaction of it. So if through photosynthesis, if the glucose is produced, then in the cellular respiration, the glucose is decomposed and it's producing carbon dioxide and water. Through the photosynthesis process, the energy is absorbed from the sun, and in the cellular respiration, the energy is released into the environment. The two reactions which I strongly recommend you to remember and to memorize for the time being, I will suggest you to write them into data booklets so that you memorize them, is as follow. For the cellular respiration, the glucose is decomposed, is burned into reacting with oxygen to produce carbon dioxide and water, as well as energy. And this is huge energy, is 2,802.7 kilojoules, is huge. And as you see, the photosynthesis reaction is the opposite of it. So whatever was as a product for the cellular respiration, now it is as a reactant in the photosynthesis, and whatever was a reactant in photosynthesis is a product on the cellular respiration. Okay, so on the first case, when we see the photosynthesis, which produces glucose, the energy is absorbed from the sun, and it's known as the solar energy to produce glucose, and on the other case, it is released in the environment. As you notice here, we will see some compounds like C and H and O in a lot of cases. We'll see some compounds that are known as the hydrocarbon compounds. Those compounds have, let's talk a bit about the hydrocarbon. Those compounds are on the form carbon with a number, and then we have hydrogen with another number, which may be the same, but still, just to make it distinguish, we say Y. And on some of the cases, we will see oxygen as Z. Oxygen is not always present, but in some of the cases, it is present. So when we see, let's say, this compound, CCH, and OH is here. As you see here, this compound has two carbons, so carbon is 2, hydrogen 1, 2, 3, 4, 5 as hydrogen on their own 5, and then we have one hydroxide here. This compound, this hydrocarbon, it's called ethanol. You can check it even in your in your data booklet, when you will see on page 4 and 5, you will see that ethanol has this formula. Sometimes this formula is written on the form C2H6O because this H is combined with the other hydrogens. The hydrogen on the hydroxide is combined with the singled out hydrogen to say that instead of 5 we have 6. And this way of writing this compound is not always the best way to, but still it's kind of acceptable, especially for students that are on the on chemistry 20. So when we see hydrocarbon, we can see something like CH4, which is again a hydrocarbon compound. And this CH4 is known as a methane, which is used into heating as a natural gas. Okay, methane and natural gas are the same, are identical. Okay, another thing that we use in terms of the hydrocarbon is the gasoline, which we use it in our cars and the vehicles to move from point A to point B. And the formula for gasoline, the hydrocarbon formula for gasoline is C8H18. So this is gasoline, and it is used in our everyday when we go and fill up the cars in the gas stations. So in everything that we see here, either in the reactions that we see for cellular respiration or photosynthesis, what do we see is either a combustion reaction or it is a formation of the hydrocarbon. In the case of the cellular respiration, is a combustion reaction, okay? Because combustion reaction. Because remember what we have said in terms of the types of reaction, when a hydrocarbon is reacting with oxygen, is forming as a product carbon dioxide and water. And this is a perfect example, a cellular respiration which happened in the trees, in greenery and the trees that we see. The glucose that is within the chlorophyll and all that stuff that is from bio, it is combined with the oxygen, is absorbing the oxygen of the air, and it is releasing carbon dioxide and water. On the other hand, what is happening at the photosynthesis is the formation of the hydrocarbon, which is a source of energy. So this is known as the chemical energy. We mentioned the solar energy, which is the energy coming from the sun. The chemical energy is stored into the bonds of the hydrocarbons. Okay. Even from science 10, you know that there are two fundamental types of energy: is the kinetic energy and potential energy. What you have seen on Science 10 and probably on the other courses is that kinetic energies are related to the motion. Now, in thermochemistry, the kinetic energy is related to the temperature of the object. So the exact formula is temperature is 2/3 of the kinetic energy that the object has and something else. However, in what we need to know is that the kinetic energy is related to the temperature of the object. If a system or an object has a high temperature, is hot, it's becoming hotter, then the kinetic energy of the uh, object or of the system is increased. And if uh, the object is becoming cooler than prior, then kinetic energy of the object or of the system, it is decreased. Temperature is the related to the kinetic energy, but they are not the same things. Even if you take a look at the units for temperature are degrees Celsius versus the units for energy, and in this case, even the uh, kinetic energy is joules. In the other hand, the potential energy, and in general, it's every potential energy, is stored, and in our case, for the chemistry, for thermochemistry part of it, the potential energy is stored in the chemical bonds. Now, when we talk about the the temperature, then you can say it in different forms of it. You can say that what is the temperature, which is the average kinetic energy of the whole system, and it is 2/3 of it. Thermal energy is the total kinetic energy of every entity that the system has, and heat is the energy that is being transferred from one object to the other, while the potential energy is energy that is stored. It's potential to happen. So as long as a hydrocarbon, in our case, from the perspective of chemistry, as long as a hydrocarbon is staying as it is, nothing is happening with it, it's not um, absorbing, is not able to react with the oxygen, then this energy, in the case of photosynthesis or cellular respiration, is stored into the chemical bond of the hydrocarbon. And as we said, even on the previous slide here, the um, plants and dead animals, through time, pressure, and heat, are storing that potential energy within the bonds. Okay, so the potential energy is part of it's stored into the chemical bonds, while kinetic energy is uh, is reflected into the temperature of the object or the system. Okay. So this discussion now brings us into what is thermochemistry? Thermochemistry is the study of heat change in the chemical reaction. In order to analyze the energy changes associated with chemical reaction, we must first define, have an agreement of the system or the specific part of the universe uh, that is our interest in. So when we are talking about system, then we can say that the system in chemistry includes substances involved in the chemical and the physical changes. For example, when we have an acid and base neutralization experiment, the system may be a beaker containing, let's say, 50 milliliters of hydrochloric acid, to which are added 50 milliliters of sodium hydroxide. The surrounding is the rest of the system outside, the rest of the universe outside the system. So what we have here is, in our case, this is the chemical system. And in this chemical system, based on the example that we just said, we have 50 milliliters of hydrochloric acid and 50 milliliters of, we are adding here 50 milliliters of hydrochloric acid, and then we are adding 50 milliliters of sodium hydroxide, and then whatever is happening within the beaker is part of our chemical system. The rest is the surrounding. I think that I spelled it surrounding. Okay, so now the first law, it's whatever. There are three types of systems accepted in science. There are three types of system. It is that is known as the open system. And in an open system, mass and energy can exchange, are interchangeable. They can change, they can increase, they can decrease, are changing. The second type of system is that is known as the isolated system. And in an isolated system, neither mass or energy are changed. So mass and energy are fixed, are not changing, are not transferred, are not allowed to transfer. And the third type of system, which is between those two, and it is known as the closed system. And on this system, the energy is allowed to move, to transfer from one part to the other. So mass is not transferable. But energy is allowed to transfer, is moving. Is transferred. So just keep in mind here that in an open system ideally doesn't exist, or in isolated system ideally exists, but actually in reality doesn't exist, because mass and energy are transferring from one part to the other. But when we see, depend on how we see it from. What we will see in most of the cases is a closed system in which mass is not transferred, but the energy is transferring from one object to the other, from the chemical system to the surrounding, or from the surrounding to the chemical system. So let's suppose that we are looking at the formation of water. So when we look at the formation of water, what do we see is that hydrogen in the gas form plus oxygen, again in the gas form, are producing water, okay, in a liquid form. If we balance it, then we will have 2 for hydrogen, 2 for water, and then we will have energy on the product side of it. In this case, we label the reacting mixture, hydrogen and oxygen, as the system, and the rest of the universe is the surrounding. Because energy cannot be created or destroyed, which is the first law of thermodynamics. So the energy cannot be created and or destroyed, but is transformed from one form on the or the other. Any lost energy of the system will be the gain energy of the surrounding, or any lost of the surrounding energy of the surrounding will be gain of the system. So now how do we see this? Let's suppose that we have again a chemical system here. It can be anything. It can be, as in the case that we saw, 50 milliliters of hydrochloric acid and sodium hydroxide, or it can be in the form of hydrogen and oxygen to produce water. So what this is the chemical system. If the energy is going to the surrounding, so the energy is moving from the chemical system to the surrounding, the energy from the chemical system to the surrounding, what will happen? The surrounding will become, therefore, the surrounding will become hot, which means that the kinetic energy, because kinetic energy and temperature are related to each other, of the surrounding is increased. Or in the other word, the temperature of the surrounding is increased. However, if we have the case when the energy is moving from the surrounding to the system, and again, the chemical system can be anything, but the energy is moving from the surrounding to the system, to the chemical system, then what is happening is the surrounding is becoming cooler. Cooler, which, as we said, again, the same thing, as we said, it is related to the temperature, so the kinetic energy, so the kinetic energy of the surrounding is going down. Or in the other words, the temperature of the surrounding is decreased. So now, the reaction is an example of this water, hydrogen and water, is an example of an exothermic reaction, because what the name exothermic or endothermic are based on what is happening with the system. So if the system is releasing energy to the surrounding, to the environment, then or it's going in the product side, then what the system is doing is exiting the energy. So the chemical system is exiting the energy, making it exothermic reaction. But when the system is absorbing the energy or is needing energy in order to complete that reaction, then what is happening is that it is adding into. So exo and endo are Greek words, which means outside and within. Exo means outside, it's going outside, and endo means in within. Okay, so this is in terms of the endo and exothermic, the terms of endo and exothermic reaction. Here's kind of a summary of what an exothermic change will happen. So the energy is produced or given by the reactant, is released into the surrounding, and it's causing the surrounding to warm up. Combustion, hot pack, and cellular respiration are examples of the exothermic reactions or changes. Energy becomes a term in the on the right hand side, or it's on the side of the products. While when we are dealing with an endothermic reaction, what is happening is that the energy is on the reactant part of it. Let me open it. So when we have an endothermic change in the system, always we refer to the system or the chemical system, then the energy is required, is added to the reactant in order for the reaction to appear. And then it's absorbing this energy from the surrounding. In this way, what it is happening is the kinetic energy of the surrounding is decreased, and the temperature is decreased as well, because temperature and kinetic energy are direct proportion of each other. So what do we see in the endothermic reaction is that the energy is on the reactant side of the reaction. This brings us into the first law of thermodynamics, which is that the energy cannot, you have heard this law even before, the energy cannot be converted from, can be converted from one form to the other, cannot be destroyed, cannot be created, but it can be transferred from one form to the other. Now, how do we know? This is impossible to prove. However, for the first law of thermodynamics, what it is that uh, the total energy contained into the universe is we see the change. So what we are saying here is that the potential energy that is stored into the chemical bond, if that chemical bond is um, is broken, then the energy is released into the environment in terms of the uh, kinetic energy, which will result into an increase of the temperature of the surrounding. So what we are saying here is that potential energy is a negative kinetic energy. Very often you can say it as EP is equal to negative EK. And then what it is that the sum of the two is equal to 0. So EP plus EK is equal to 0. How do we translate this into thermochemistry? Is EP is the potential energy stored into the surroundings. So that means that the energy of the system, of the chemical system, plus the energy of the surrounding, because kinetic energy is related to the temperature of the surrounding. So the energy of the surrounding will be equal to 0. Okay, so in other words, when we see this reaction here, we can express it as being on the other side. So what is happening with a negative sign? So what is happening to the surrounding? The surrounding is losing kinetic energy because the reactants are needing or gaining potential energy. So here is the law of thermodynamics. The energy cannot be created or destroyed. The heat always flows from hot to cold, and the total heat or energy lost is equal to total heat or energy gained. Those are the three laws of thermodynamics. In terms of the fact, what is the which one is endothermic or exothermic, where is the energy going to be displayed into the reactant or into the product side, is the first law of thermodynamics. Then the second one is telling us, it's not quite applicable here, but it is telling that the energy, kinetic energy, flows from hot to cold, so until it reaches the equilibrium. And the other one, which we will use a lot, is especially on the calorimeter, is total heat loss, total energy loss is equal to the energy gain, or heat loss is equal to heat gain. Okay, this concludes the first day of the thermochemistry, or the first part of the first day of the thermochemistry unit, and we will deal with the second part of the first day, which is calorimeter, and then we will see the assumptions and everything that is related to calorimeter. So let's have a break, and then we'll see each other in a bit.